universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to SkyTour Radio. Oh, there you are. Hey, everybody. It's Mark D'Antonio here with SkyTour Radio, and I want to welcome you-know-who, Mr. Astronomer down there, Daryl. Hey, how's it going down there, Daryl?
Hello, Mark. I'm fine, thanks. How are you? Hello, Amanda.
Hi, Daryl.
Right there, yeah.
Oh, surprise. I'm here, too.
Yeah, of course you are. So, welcome. We have been having a banner couple of weeks at SkyTour Livestream Observatory out in the desert in Arizona.
I want a raise.
Daryl wants a raise. I'll tell you what else. So do I.
Mark actually gave me the night off last night.
I did because
I can raise them on the screen.
Oh,
promotion.
Actually, we can do better than that, can't we? We can move Daryl over here, and now see he's in the lead. So, Daryl, what are we doing tonight?
We are going to take a tour of the sky and see lots of neat dark sky stuff that somebody I know took pictures of.
Really?
And
that's
I think we're going to talk about the Webb telescope also.
Yeah, we are. Exactly so. And you know what? We're very excited. Daryl and I are both excited. We're going to actually stream when the Webb telescope gets launched in just a few weeks, actually a couple of days, 23 days, actually.
Yeah, I'll believe it when I see
counting.
You know, there's a countdown clock online. I go to it and they go, yes, come on, go. You're going to go. You're not going to be delayed again. I can tell you that. Well, hey, you know what? We're going to try, right? So, there's a lot of people that come here to SkyTour Radio, and they also go to SkyTour Livestream. Everything's SkyTour. It's all things SkyTour. And what is SkyTour? SkyTour Radio and SkyTour Livestream are a place that you can go to actually learn about astronomy. In SkyTour Livestream, it's a live deep sky observatory out in the Arizona desert. We also have an observatory here on the East Coast. We have one on each side of the continent. And SkyTour East is being rehabbed. We're working on it right now to get it up and running. And just to get an idea of what it looks like or what it will look like, okay, if I just do this, you can see behind me right there, actually right there, you can see the telescope for SkyTour East right there. It's sitting on the table, getting ready for installation in the new building once the new building is complete. With everything, the cost of wood has been phenomenally outrageous, so we haven't actually started building the building yet. We've had to get the wood and everything taken care of. It's just everything's so expensive. But SkyTour East will be out here. That particular telescope is going to do some different things than SkyTour West is doing. And SkyTour West is predominantly a visual journey into the evening sky, the deep sky. And when we watch the things that we look at in that sky appear right before our eyes, it's stunning. We see beautiful nebulae, which are the sources of new stars and thus new planets down the line. We see phenomena in the universe like hot stars that blow off their outer layers, leaving these very cool gaseous nebulae that glow because of the high radiation coming from that leftover star in the middle. We see clusters of stars that formed once in a nebula, but then blew away all that gas with their stellar winds, just like our sun has a stellar wind. Okay, our solar wind causes things like the auroras that we see here, the auroras that we can see on Jupiter, the auroras that are on Uranus and Neptune and other planets and Saturn, and so forth. So, we can see a lot of these different things in our SkyTour Livestream Observatory, and then we talk about it, guess where? Right here on SkyTour Radio. SkyTour Radio is your journey into astronomy as well. And I'm an astronomer. This is what we look like, and I'm actually dressed for the occasion because, it's somewhat cold here. We actually had snow here today. So, as a tribute to all those that have to endure the winter, I too am dressing to endure the winter for you tonight.
Yeah, sunny and 60s here today.
I don't want to hear that. I
It'll
mean,
be even nicer
that's
tomorrow.
nice. That's nice, Daryl.
Well, you know what it's like. I mean, you've been virtually hanging out in Arizona a whole lot lately. We all have, and
Yeah.
It's even nicer down there, but it's nice here.
Yeah, that's for now. It is. It is. So, and Amanda, I really want you to come back and hang out with us on Skytour live stream. I want you to be part of this. And you've been absent for so long that we've forgotten your name.
Oh no!
No, I'm kidding. I know you're very busy, and you've got new duties with KGRA and KGRA-DB. So you're actually really, you must be raking in the big bucks, huh?
Oh yeah, I'm on signing Daryl's petition for a raise.
Well, if you get twice what you're being paid now, you're still probably going to have zero.
Yeah.
And so will I. But you know what? The privilege of being able to explore the universe and share it with everybody is really where I'm coming from.
Well, I'm getting a free education and, have direct access to ask a proper astronomer or anything I want. So think of how much money I'd be in debt if I was taking a course on this somewhere, going to school for this. How much were you in debt, Mark? And let's inflate that from the time you were in school. I think I'm well compensated.
Yeah, back when I got my degree, when I left school with my astronomy degree, I was thousands and thousands and thousands of dollars in debt, and I had to work it off and pay it down over time.
And you're still not even charging people to come to this show. Skytour live stream is free on YouTube. You can check in here every Sunday. It's a live show. Take advantage.
Skytour Radio is, yeah.
Skytour Radio on KGRA, yep. But you have the guys here, you have the minds here, so pick them.
I know that's true, man. And all of you watching and listening, we have wonderful people. You may have noticed there's an extra bubble missing tonight, and that's Tara. Tara is usually one of the four here, and she is away on vacation. And I didn't have the heart to say, please come in today, because she is basking in the sun. I should have had the heart to ask her, huh? And why should she have that? Look at me. I'm dressed up for the winter. She's out there. So nice out. It's like, I don't know. But I guess that's what happens, right? So you know what? So tonight what we're going to do is, it's going to be a little different tonight, because we're going to actually take a little journey through the night sky, courtesy of Daryl. We're going to have Daryl do the typical Stellarium deep sky. We call it Deep Dive with Daryl. And we're going to stop every so often, and we're going to explore some of the objects that we've taken. I was out in Arizona, fixing a slight problem with the telescope. If you remember when the Hubble first went up, the Hubble Space Telescope was myopic. It was as if its glasses were on like this, It couldn't really see straight, and everything was kind of fuzzy and had artifacts, as they call them, in the vision of the Hubble. Well, they fixed that with a shuttle mission. They gave Hubble glasses, and those corrective lenses fixed Hubble's problem. And it went on for well over a decade or more so far to bring us these actually several decades, to bring us these amazing photos that it's taken. And so we've kind of learned our lesson in that as a human race. And now we don't send up anything into space until we know it's ready. So that is probably why the James Webb Space Telescope has taken so long. You not just double and triple check, you check your double checks, you check your triple checks several times. And so they've been very, very careful, because the James Webb is simply not going to be in a location where we can service it if it goes bad. It's going to be about a million miles away at what's called a Lagrange point, which is sort of like a parking spot in space. Very little fuel is needed to keep it at that spot, because all the forces of gravity from all the surrounding bodies in the solar system kind of sum to zero at that point. And it's sort of like that little dead spot. So it's like a mountaintop that's pointy at the top, but there's a little bit of a flat spot on the top. As long as you don't go too far off that flat spot, you won't fall off the sides. And so that's what a Lagrange point is. It's a little flat spot on the top of a steep peak. Okay, you go too far to one side and you're done for, and you're going to take off in another direction. So we don't have that problem.
I bet you
James
dollars
Webb.
to donuts we're going to have to go to the Lagrange point sooner or later. I wouldn't be surprised if it was sooner, knowing the web's history. And all I can hope for at this point is that Elon Musk will get us there.
Well, that's true. I mean, if you think about it, service missions to orbit are costly. To launch the shuttle back when it was launching and flying was around $22 million to get it off the ground. And then you had all of the people on board the shuttle, the crew, and then it was risky. I mean, space travel is still the riskiest possibility, the riskiest endeavor for the human race. But I think, Daryl, you might be right. Yeah, I'll tell you why. I've mentioned this on the streams. I've mentioned this in posts. I've mentioned this in interviews and talks all over the place. Space is in the process of being normalized for us all. What that means is, in the past, like say go back to the Apollo missions, and yes, we landed on the moon. Okay, if you go back to the Apollo missions, the astronauts that flew were only very rigorously trained Air Force personnel and pilots. Okay, they're the only ones that could fly and go to space. That's because going to space required so much attentiveness, so much interaction, so much understanding of space flight systems. Nowadays, people go for the ride. I mean, look at William Shatner. He's the oldest man to ever go to space. Now, okay, you argue, well, it wasn't space. Well, it was. It was above what's called the Kármán line, okay, which is a established definition we have for where the Earth atmosphere ends and space actually begins, okay? And he was the first 90-year-old, the only 90-year-old ever to go that high in space, that high into what we call space. Now, yes, the New Shepard spacecraft was just a big flying pencil going up and then going down, okay? So it didn't enter orbit. It didn't orbit the Earth. It just went up and then down. But the process of space, the process of going to these extents is being normalized for us all. Now, you might say, well, only the rich go to space. Yeah, well, you know, have Shatner, he's a millionaire, gets to go to space. Bezos, billionaire. And you say, well, all these bad things about it. But guess what? That's what they were saying about the developer of the TV. That's what they were saying about the developer of the phone. That's what they were saying about the developers of the radio and the cars and any big technological advancement. That's what they were saying about them. And now we have a phone, okay, that actually makes a phone call, but it also does thousands of other things, okay? This is normalized. You show this to another person and say, look, I have a phone that does all these really cool things. And they'll look at you and go, yeah, so everybody does. That's a key point. Everybody does. And so over time, traveling into space will also be normalized. I see the day, and I'm sure you do, and you do too, Amanda. I see the day when you'll have a father of 3, a mother of 6, saying to their family, you know, I'm sorry, guys, I have to go to the moon. Ugh, there's a satellite up there that's on the fritz, and I'm the only one that can fix it. So my team has to go up and fix it. Oh, Ma. Yeah, I'll be back in 6 days. Ugh, all right. Can you at least send us a postcard? Oh, yeah, I'll call you from the moon. That's going to happen because industry is moving into space. And when it does, you're going to have need for people who can mine. You're going to need people that are computer science people. You're going to have need for engineers. You're going to have need for people to do grunt work. You're going to have the need for people, period. And they're all going to have to go and then work. And maybe at first it's going to be, wow, I get extraordinary pay to go to the moon. Ooh. It's like drivers in Iraq. Drivers pulling down $200,000 for driving supplies in Iraq. Okay, well, you're going to have the same thing, but in orbit around the Earth, servicing satellites, the same thing on the moon. There'll be established colonies on the moon, locations where on the moon you will fly into, and then just get used to it for a couple of days. Yep. And I think that's going to happen. I think it's going to happen.
It'll be like the moon is a harsh mistress one of these days. A lot of working class Joes on the moon.
That's exactly right. And don't forget, we've done this before.
Then they'll want independence.
Right. How have we done this before? We've done this before because we plied the vast gulf between continents. We went from Europe to the Americas. And that was a journey that had no guarantees. So you see, we do it in these bite-sized steps. And this relates to kind of like the first chapter of my book, The Populated Universe. I talk about the problem with the numbers and how big things can get very quickly. But I also talk about scales of things. To an infant in his crib, the entire world is the face of his or her mother coming down to him and the bars of the crib. When they learn to stand, their entire world is what they see over the bars. You see the room, the walls. That's their whole world. And maybe they get in mom's arms and they walk around the house for a while. Okay, and they see the rest of the house. Then when they can walk, they go to a window. And now their world becomes not just the house and the rooms within it, but what's that? There's a yard. And who's that? What's that? It's a bicycle. Wow. And then they get old enough to ride a bike and go outside and play. And now the limits of their universe are their yard. And little by little, that expands. Then when they learn to ride a bike, their limits of their universe are a block or two away. Don't go too far, Johnny. Okay, Sally, you can't go too far now. Okay, and they stay within a certain distance of their house. I distinctly remember as a child not obeying that rule. And I got in a lot of trouble. But the thrill of riding farther than I was supposed to go, that stays with you. And I remember riding like a mile from my house, and my mother said, just don't go around the block, and that's it. Well, I rode around the block. I went down this long street called Tomlinson Avenue, and I got to the Plainville High School. Ooh, wow, look at this place. And went onto the fields. I was playing in the field thinking, look how far I am from home. And for a moment, I thought, I hope I remember how to get home. Which way is it again? Okay. And I figured it out, and I knew I could get home. So you see, it's called pushing our limits. And that's what we do as a human species. We do it as toddlers and on up. And now what's normal for us is to fly across the country or fly around the world. Fewer people fly around the world. Okay. I had the opportunity to do it just once, not around, but to Norway. Okay. With a stop in Copenhagen, whatever. And I did talks over there, but this is like typically not normal. I don't do that normally, but I travel around the country an awful lot. I'm in Arizona. I was just in Colorado. I got to meet Katie Grabowski, who's the Mutual UFO Network's state director in Colorado. A real sweet lady, and lots of wonderful people there that listened to a talk I did. Well, you go to these different places, and that's normal for us. That's normal. Normalized. Right? Well, don't forget a time when flying on a jet was very expensive, and it wasn't for everybody. In the beginning, it was only Air Force pilots that could fly jets, right? You could not sit in the backseat of a fighter, no way. And when they started making passenger transport, well, that technology developed over time and developed to become a multi-billion-dollar industry that it is today. The end result is profits drive progress. Okay. So if you can profit from it, you can bet your buns that they're going to actually build an industry around it. And the moon is full of incredible amounts of raw materials that we want here. Okay. The moon has lots of helium-3. Now, what's helium-3 and what's the 3 mean? Well, it just means that's a helium with an extra neutron in its nucleus. What's that mean? It means it's an isotope. Okay, helium-4 is 2 neutrons. Because why is that? Because helium has 2 protons and 2 electrons normally, and they're happily going around. The electrons happily going around. Okay, but that is a normal helium atom. If you add a neutron to a helium atom, it doesn't have any charge. It just adds mass, and that becomes an isotope. That is a variation of the original helium, and so thus these helium isotope is the kind of thing that we would use, for instance, to do nuclear fusion. Once we get to the point where we can do fusion processes, and we may or may not, okay, then helium-3, of which the moon has in abundance, is a really, really good shortcutting step to getting nuclear, fusion fuel, because we'd have to first make the helium-3 to then make a fusion process happen. Helium-3 is sort of a fuel. If we can get it without having to do anything to it, well, then that saves us a ton of processes, a ton of energy, and we get even more out of the final process. So that's why helium-3 is so attractive to us. So whether that's going to be or whether that's not, remains to be seen. Okay, I don't know how much about fusion Daryl knows, but I do know that fusion is a process that's going to take an awful lot of experimentation, an awful lot of further study. I know
only 30 years away. It's
and
always only 30 years away.
Yeah, and one time it was only 10 years away, and it ended up being 30 more years away after that. In the same regard, we're heading toward it, and there's a lot of problems with it because that's the energy that the sun uses. Well, you know how hot the sun is. We don't have a container that can hold a sustained reaction to make that happen on this planet. We just don't have any materials that won't melt at the temperatures required for fusion to take hold. So we've done fusion in the laboratory, but we've done it at a very limited basis and just a little reaction at a time. And that's it. So we have a ways to go. So the moon is attractive.
I'm sorry, they are getting a net plus on the energy side now, aren't they? In experiments.
I'm hesitant to comment on that because I haven't looked at the latest stuff. I do know that there were claims that they're getting a net positive result, but I don't know how that's possible with all the energy they have to put into it yet. So I don't know.
Yeah, well, I've heard the claims. They say they're getting more out than they're putting in.
I'll believe it when I see that. Just like you'll believe that the James Webb is going to launch when it happens, right?
I was going to say.
We actually have a question from chat.
Sure.
Just on what you're talking about with the fusion, I assume. He wants to know, why did tritium start being called H3?
Oh, well, okay. If you look, that's a very good question, Charles. Here's what you got. Okay, hydrogen. All right. If you look at hydrogen, okay, the hydrogen atom has one proton and one electron, right? If you add one neutron to the hydrogen nucleus, right? If you look at that extra neutron in the nucleus, that becomes deuterium. Okay, deuterium is what we're calling this isotope of hydrogen. Okay, all right. Now tritium is different. Tritium is actually the same kind of thing with another neutron. So that's why they're calling it H3. In a sense, right? Because and you got to be careful. It's not H2 like a diatomic molecule, hydrogen. Hydrogen, when we talk about deuterium, it's actually notated differently. It's an H with a 3 up above and not down below, indicating 3 atoms of hydrogen. So that's
its mass is 3, correct?
If you
one proton, 2 neutrons, that would add up to a weight of 3.
That's correct from a nuclear point of view. That's right. But that's the whole point with tritium. And the thing about tritium is also a byproduct of fusion as well as an input product. So if you actually do fusion successfully, tritium is a result. And guess what? You can have powdered tritium in your hands, rub it between your fingers, rub it on your hands, rub it on your arms, rub your face with it. I know that sounds crazy because tritium is mildly radioactive. But guess what? It will not soak into your skin. It won't poison you. All right. It's not one of these things that can kill you as well. If you bathe in it, it will eventually hurt you. But I don't think that when you look at how tritium affects the body, the fusion products are far less dangerous than fission products. What's fission? Well, fission is like the Fukushima reactor, where you have these nuclear fuel rods and they're full of pellets. And these pellets, because they're in proximity to other similar rods that have those pellets in them, they react with each other. They cause a nuclear reaction and they heat up water. That's all these nuclear reactors do is heat up water. Okay. So it's kind of interesting. And that heating process is stopped by dropping these inert rods down between the active fuel rods, which shields them from each other and starts to meter the reaction, shuts it down, brings it up, whatever. That process, though, in a fission reactor, if it fails, then you can get what's called a meltdown. And that is the meltdown process that is something we saw at Fukushima, and part of the problem that happened at Chernobyl. So that said, and Chernobyl was a different type of reactor than Fukushima. However, the Fukushima reactor blew up not because of a nuclear explosion. It blew up because in the building, you can see a shockwave and you see the whole building blow up. Actually, the building was designed to blow up. I know that sounds crazy, but it was designed to blow its top rather than have a catastrophic explosion that could do additional damage. And that building design was such that hydrogen gas built up in the building. And then when it went off, it blew the top off the building. And that's exactly what you saw. You even saw a shockwave. And it was really, really a powerful explosion. But it wasn't as dangerous as it could have been. Even so, the ground for miles around was irradiated by this fallout. And that's the fission process. You know, I look at fission like this. Fission is a process where you're looking down the bottom of a well, okay, at bottom of a very, very steep valley, okay, hits it like that way. The fusion reactor is at the bottom. And to make it stop, you have to push it up the sides and perch it at the top. Pushing it up the sides is the equivalent of dropping those rods down in between the fuel rods to slow down the reaction. That's what pushing the sides. If you have to add energy to the system to shut it down, okay? Fusion, on the other hand, the fusion process is like this. It's like a sharply pointed hilltop. And at the very top, you have a reaction teetering. It's always it can almost go out every single time. And your job is to keep it balanced at the top. The slightest imbalance, unlike Fukushima and unlike other fission reactors, the slightest imbalance, shuts down the reaction. No meltdown, no explosions, no bad output chemicals of any kind. So that's the difference between fusion and fission. Fission is a filthy, dirty fuel with many problems with the leftover components, the waste products. And fusion, on the other hand, is clean. Fusion is clean, you know? So I think
hope that answers.
What's that?
I hope that answers Charles's question.
Well, I think so. We're talking about a bunch of things there. Okay.
Yeah.
And I know and the chat's going crazy. There's a bunch of people in there that are trolling because they don't like something that I.
You saw that, did you?
Oh, I saw that. I know.
I'm trying to shield you from.
No, you don't have to shield me. I know who it is, and I know that he's just never been happy with my answer because he refuses to believe that there can be reflections in windows. Just because it's in space, there's no reflections in windows, apparently. Well,
okay. Well, I don't know anything about science, but I understand glass reflects. Okay.
Yeah, no, and that's fine because and I don't mind. Like I said, I can't make everybody happy, and I often don't. And you know what? I'm all right with that. You know, if you don't science, that's not my fault. I'll be happy to explain it, and if you don't accept the explanation, well, then that's where you believe in non-science, or as I say, nonsense. Okay. So people who go through life science-free, unless it's because they simply don't know, then I have a problem with it. You know, the people, for instance, that actually will look at something and have a critical approach, critically think. Those are the people that I take the time to explain things to, and we have a discourse, we have a discussion. But someone who makes pronouncements and says, this is a UFO, maybe, and I'm not unwilling to say that's true. Yeah. But if I don't think it is, and I see reasons why it's not, and I can point out reasons why it's not, I'm not saying it's not. I'm saying it might be this. And that's all I ever said in this particular case that the guy in chat is going crazy with. Okay. And I'm sure he's happy that we're talking about it too. But I'm not going to bring it up. I'm not going to name him because I don't want to give him the time. Okay. It's just what happens, when you do this stuff. So that's fine. If you want to know what he's talking about, then you'll wait for him to attack me in Facebook at some point. You'll see it happen. And you know what we're talking about. Okay. But that all said,
I'm gonna look up that number. What an STS number.
yeah, that's a space shuttle mission. Yeah.
Yeah. I'm gonna look into that after the show.
Fine. That's fine. You know?
Mm.
So anyway, all these things that we're talking about are related to moving the human race forward, right? So that's something that I think we're going to end up doing, and we're going to be doing it rather in spurts, let's say, because we reached something called singularities. Micah Hanks, a good friend, okay, he wrote a book on singularities, and it's quite good. And so you might want to talk about look up his book on singularities, okay? As we advance, we get to the point where we can't just brute force something, think something through, and get the answer. We have to depend on artificial intelligence and systems that kind of leap ahead and that leap ahead in a way that we can't reach. When that happens, we've kind of given in and given over to advanced technology to do the work for us. I mean, that doesn't sound too crazy to you, because right now we know that a pilot and a co-pilot can't fly a jet without all the additional systems that the jet has. Okay, they have their collision avoidance system. They have other systems. They have the engine systems and computers in each engine to monitor and control things, oil pressure, all these things. They have a lot of features that they can't manage manually, so they have to trust that their systems work right. And sometimes we've seen, sadly, that they don't, and planes go down, you know. But the fact is, we're doing more and more of that. And as we get more advanced, we're going to have to do that even more. James Webb Telescope is an example of a system that is going to have to be pretty much autonomous. It's going to have to be able to fix whatever may go wrong within it, because we can't go there. As Daryl said, maybe we will, but I'm not sure. You know, we may not be able to get there. So I just have to say that, you know, that telescope, when it launches, I'm already nervous. Just if you couldn't figure it out, I mean, I'm kind of nervous because the James Webb has some tremendous capabilities, and it's going to be just an astonishing system once it gets up into space.
I think
go ahead, Daryl.
I'm sorry. I think I wonder if some people are going to be disappointed if and when the Webb starts producing results. I shared that floating along the Milky Way video with Isabella and the chat at the live stream the other night. Isabella seemed rather taken aback by it. She couldn't recognize anything. It looked so unfamiliar to her at infrared.
Mm-hmm. Yeah,
and the Webb is an infrared telescope. And
yeah.
I just wonder if people are really going to be able to relate to the infrared images, because it's going to be a mind blower, but it's going to look so different. Are they really going to be able to relate to it?
No, that's the thing. Okay. And that's sort of a good segue to go into the Webb here, Daryl. I mean, the James Webb Space Telescope is actually a telescope we've been working on it for years, and getting it ready. And this is the telescope itself right here. Okay. If you look at the telescope, you can see there's a large pink thing on the bottom. Okay. And then you see that gold thing on the top with the circular shape to it, rough circular shape. That's actually the mirrors. And these mirrors are far and away way bigger than the Hubble. This is a 21.3 foot diameter mirror set. And normally we have been, and I'll bring it back up, we've been constrained to launch only things that can fit inside a rocket tube. Okay. And the biggest rocket tube we had was around, 8 or 10 feet or so. And we had to actually have whatever fit in there, a mirror had to be in there. You can't take a mirror and turn it on its side and get it to fit in something bigger than the diameter, because the diameter is the same all the way around. So no matter how you try and fit that circular thing in a tube, that tube has to be bigger than the circular mirror. And to this point, we hadn't had that. Okay. So what the James Webb has done is rather unique. If you look at those mirrors, Each of those mirrors is a hexagon, a six-sided, faceted object. And these mirrors actually fold up. They fold up. And when they fold up, it means that we can put a 21-foot mirror in a very small package. And that's exactly what we're doing. However, what it also does is it makes it really difficult to depend on the unfolding technology. You have to really test it over and over. And you can't test in zero gravity here on the planet. Okay. You have to simulate it. So to test this with the James Webb, they had these wires up above it, and these wires would suspend some of the parts and take the weight off so that it could simulate opening in zero gravity. If we had anti-gravity, well, then we'd have no problem. We just unfold it in a zero gravity chamber and hey, okay, it works fine. Stick it in the rocket and go. But we can't do that, you know? So we have to test it under Earth gravity, and sometimes the tests work and sometimes they don't. They make adjustments, and when they do work with the simulated zero gravity, you still don't know if it's going to work once it gets into true zero gravity, okay, or we call microgravity. But the Webb, on the other hand, will be in true zero gravity because it's going to be far enough away where it's not orbiting a planet, where it has to kind of be accelerating around a sphere and it's basically falling with style as it goes around the planet. Okay, so this is going to be a very different situation. I'm very impressed with the construction of the Webb, and that pink thing on the bottom is actually a sun shield, as it says there on the right side. And that's unfolding. It's a very thin thing, but what it is there for is because the Webb, as Daryl pointed out, is an infrared telescope. It's going to be handling and viewing infrared light that's coming from a part of the spectrum that only part of which we can see with our eyes. And it's a deep red part of the spectrum. And I'll show you that shortly. But the thing about the Webb is that the infrared detectors, if you think about it, what's infrared energy? It's heat. Okay. And what in our solar system has copious amounts of heat? Well, yes, most of you are saying the sun, you know, well, also the moon and also the earth and also every other body in the solar system gives off heat. And the Webb can detect all of that. It'd be like the loudest noise. Okay. The heat coming off of the cloud tops of Jupiter would be enough to overload its sensors. Just imagine. So this sun shield is more than just a sun shield. It's actually going to shield it from the planets as well. That's always going to be facing to where the objects that will be affecting it the most are located, mostly the sun. Okay. And if you look on the top, just behind to the left, where it says back plane back there, you see that integrated systems instrument module, that ISIM. Okay. Well, that ISIM is composed of several instruments. All right. And one of those instruments is something called NIRCam. Now, it doesn't mean NEAR. It means NIR cam. That's near infrared camera. And that is a camera that's going to see in what we call millionths of a meter. If you measure things in a millionth of a meter, then you're measuring in what's called a micron. Okay. So this is the way this looks. Okay. We're looking at a wavelengths table here in microns. Okay. That split top part, that's blue, green, red, where it says blue, green, red. That's the visible wavelengths. Okay. And to the left are the ultraviolet, X-rays, and gamma rays further out. And then to the right are the infrared and microwave and radio out that way. And the visible spectrum is in the range of, in terms of this measurement, it's just a way to measure 0.4 microns to 0.7 microns. Okay. That's the visible spectrum. Now, the near infrared camera on the James Webb is going to be able to see anything from 0.6 microns out to 5.0 microns. So what's that mean? It means that the beginning of the red end of the spectrum that we see here, all right, and on outwards. So it'll see the red visible light from 0.6 out to 5 microns where we can't see. So a little bit of what we can see, and then mostly what we can't see. Okay, and that is the eyes. That's going to be the eyes of the James Webb. Okay. Now that is just the near infrared cam, and that's why it's near infrared. It's kind of near the red end of the spectrum. Okay. Thanks, Justin T. That's very nice. And if you look at the addition of a spectrograph, that is breaking up the light we see coming from these objects into their constituent components, we will be able to detect what these things are that are making this light. So a spectrograph would allow us to see details in the light that tells us the chemical elements, for instance, that are in that emission that we're picking up. All right. There's another instrument on here, and this other instrument is also located on the back of the telescope where that integrated science instrument module, the ISIM, is. Okay. And that is called the MIRI, the mid-infrared instrument. And that measures from 5 microns, leaving off where the other one did, all the way out to 28 microns. If you notice in the diagram here, you'll see, some pretty small numbers to the left, and then you see 1. And then to the right of that is bigger numbers, right? 10 to the second, 10 squared, that's 100. So there's 1. Well, just past that is 5. And out to 28 is what the mid-infrared spectral instrument is going to look at. Okay. In addition to all this, this is the cool part, and this is why this telescope is probably going to change human history. In addition, there is an instrument called the FGS, okay, Fine Guidance Sensor, and that's coupled with the near infrared imager and near infrared slitless spectrograph. What the heck does all that mean? What it really means is we're going to be able to see basically from 0.6 to 28 microns, which is the infrared range. We're going to be able to see things like the atmospheres of exoplanets. We're going to be able to see first light detection. We're going to be able to, in other words, detect planets for the first time, discover new exoplanets. We're also going to be able to do something very important. We're going to be able to do what's called characterize exoplanets. And what does that mean? Well, characterizing exoplanets just means that we're going to be able to figure out their radius, their temperature, their mass, and whether their atmosphere could have something like oxygen, right? So oxygen is very important to life. And, when Amanda's joined us and when Daryl and I talk, we always talk about, oxygen being a most important element in the universe, along with carbon, what makes us. And, but the problem is oxygen, its lines that you can detect are in the visible part of the spectrum. Wait a minute. How are we going to see oxygen then? We're not going to see it directly. And you're going to say, well, then why are we launching this thing? Because the James Webb Telescope can do something even more important. It can show us the signature of what happens when oxygen molecules bump into each other. That gives off a specific infrared wavelength. And if we see that, we're going to know absolutely without question that there's oxygen in the planetary atmosphere. And it's actually very reliable. And there's been a lot of studies. I read there's an article in Natural Science. There's an article I just saw in the Astrophysical Journal, which talks about the possibilities of this oxygen bumping process being a primary method by which we're going to detect oxygen in an atmosphere. Now, that signal, all right, if I bring this up, that signal will occur, and that bump will actually show up at 6.4 directly micrometers. Okay, so in other words, micrometers, we call it micrometers. Okay, so just past the 1 there, okay, is going to be where 6.4 is, and that's well within the range of the James Webb. So when we look at a planet, if we see a signal at 6.4 micrometers, then that's going to mean that we're seeing a signal of colliding oxygen molecules, O2. Okay, O2. And that will tell us something about this. Now, oxygen can occur naturally. There's no reason it can't. There can be ways in which we can see oxygen occur from geology and so forth. But the way the oxygen is seen in conjunction with other elements and other compounds that we'll see in that atmosphere will tell us whether that oxygen is produced by life. Isn't that exciting? I mean, that's pretty cool, isn't it? You know? So I don't know, Daryl, if you've got anything you'd like to add there. I kind of blurting out quite a lot here. Are you, Amanda? You can, of course, say what you like, because
I have a question or two. Can you put that image, that picture of the telescope back up, please?
Sure. Wrong picture.
Okay, I'm a nuts and bolts kind of guy. It's what I do for a living. You mentioned the Integrated Science Instrument Model up there, the ISIM.
Yep.
Did they plan ahead, especially considering their experience with the Hubble and having to go up and service it a couple of 3 times? Have they made that so it can be modified, remove and switch modules and stuff? You know, imagine a space mission down the road where they go up and upgrade or repair the telescope.
Yeah.
Can they get in there and start pulling circuit cards or, solid state drives or whatever and fix or upgrade the system?
Yeah, that's actually a wonderful question. And I do know something about this because I had the same question. It's very important, obviously, to do maintenance. So when we consider to maintain an object of this stature, you can't get to it. It's a million miles away, So we're not going to be able to maintain it without some serious effort. The key here is something called redundancy. We want to have additional service items on board that aren't in use, that don't take up a lot of weight, and that can be switched to. Guess what else has those? The Hubble Space Telescope, because they thought about it way back then. The problem Hubble had is that its optics were messed up. I hate to say it, but the optics they're done here in Connecticut, where I live. The Perkin-Elmer Corporation really screwed up. But this is different from an optics problem. If you remember, the Hubble also had problems booting up recently, and they had to shut it down. What they were doing was cutting over to duplicate systems, duplicate processors they had on board, and they finally were able to get Hubble back. Okay, so there were some problems. Maybe cosmic rays took their toll. Everything you put into space has a life expectancy because of cosmic rays. So same thing here. James Webb has these redundant systems on it. They have multiple core computers that they can switch to in the event of a problem. And I mean, you can't put 20. There's probably 3. Okay. And you hope that you never have to use the second one even. And that's an issue, right? And so with James Webb, there are redundant systems as well. These integrated modules are extremely complicated, which is why the Webb Space Telescope costs so much, because of that integration. Plus, the Webb is made of technology we've never had before. We had to build these hexagonal mirrors in a way that was never done before. The Gemini telescope up in Mauna Kea in Hawaii is a faceted mirror telescope like this one, but it was never built to be folded. It was built in place with all these mirrors aligned. And the thing about a faceted telescope, thank you, Charles, for that link. Thank you. Awesome pictures of the Webb there. Yes. The faceted telescope like that up to Gemini allows us to do something else. It allows us to use something called AO. And that is an optical system that allows us to account for that's called adaptive optics, to allow us to account for the issues with the air mass that's over our heads. Warm air on a road makes a mirage. You see that little shiny thing and you think it's a water, but then you drive up to it, it's gone. Well, warm air causes disruptions in the atmosphere that can affect optical performance. So adaptive optics looks at this, uses a special laser to probe that, and then decides to change the way the mirrors are working with each other in order to sharpen the image and make a better system. Again, like normalized space travel, the adaptive optics system was only a $100,000 to a multi-million-dollar system on the most advanced observatories. Well, now you two and me, we can buy an adaptive optics system for our telescopes, like the one back there. Not quite like the one back there, but we can do that now. And that system would cost $12,000. Yes, I know that's as much as a cheap used car, but guess what? It's available for the mainstream people now. So you see, this is an example of technology that's making it into the mainstream. Same thing with this. The stuff we see with James Webb is gonna, with the redundancy of the James Webb, is going to make it into the mainstream as well, other systems. And we're going to need all this, because when we're finally having a lunar presence that's permanent, or a Martian presence that's permanent, we're going to have to take care of doing, we're going to have to take care of this. We're going to have to take care of doing all these things in a way that doesn't require attendance, and we are going to have redundancy. James Webb has redundancy, and we're good with it.
Can I jump in with another nuts and bolts sort of comment?
Sure. Do you want this back up again?
No, that's okay.
All right.
The Webb is long over time and far over budget.
Yes.
And there have been a lot of stumbling blocks along the way.
Yes.
This is why I am not filled with confidence for the upcoming launch and deployment of the telescope.
Yeah.
When they folded the telescope once as a test, fasteners started falling out of it. Nuts and bolts, screws started falling out of it. And that doesn't exactly fill me with confidence.
Yeah, I know.
Now, when they shipped the telescope down to French Guiana or wherever it is for the Ariane launch,
yes,
with the ESA, you heard about this just some days ago. Some big clamp popped.
That's right.
When it shouldn't have. I believe that clamp was part of the holding assembly for, to restrain the telescope during the launch.
Yeah.
And it released all by itself. And this is why I am not overflowing with confidence for the deployment of the Webb. Stuff like that.
I know.
And I know why they're sending it to the L2 point to get away from the Earth and the sun and stuff like that. Yeah. And but it's so far out we can't reach it if it does screw up.
Yeah, L2, by the way, guys, L2 means Lagrange point 2. We have a number of Lagrange points around the orbiting body like the Earth. And these Lagrange points, as I said, they're places in space. They're like parking spots where all the gravitational forces seem to sum to zero. And we have a couple minutes left before our break, but I did want to keep mentioning here that the Webb system is actually, these instruments are actually going to be a tremendous boon to what we do, and a tremendous advantage to helping us figure things out. So even though the clamp popped, I have confidence that the conditions under which the clamp popped will be different from the conditions of launch. I'd hate to see a jumble of golden mirrors at the bottom of a booster. Okay. And that would really be just pretty gross. I ixnay on that. Okay. I don't want to even suggest that. That's terrible. What a terrible thought. Well,
the whole general thing with, advances in technology, complexity increases. Yes. And the Webb is so much more complex than even the Hubble was. It's just there's more chances for things to go wrong.
Exactly, but keep in mind that the Perseverance rover represented a giant leap of technology and many different facets of new technologies that were being implemented. And so far, it's gone flawlessly. The delivery by the Sky Crane to Mars was perfect. It was flawless. I watched it live. I was like this, because I'm a nerd. Look at me. I'm a geek. Okay. I'll tell you, though, it's quite an amazing place to explore, and the universe is at our feet once we get the Webb up there. But we'll continue this on the other side of our break. I hope you guys stick with us here on SkyTour Radio. And we haven't heard a lot from Amanda, but maybe we'll turn the show over to her on the other side of this. What do you think, Amanda?
you want them coming back after the break, don't you?
Oh,
Don't threaten our viewers.
They're funny. Stick with us, guys. We'll be right back.
I flew across country, got my manual, and I was ready to go. It starts with some classroom time and hearing expert advice from MUFON field investigators.
I'm Gwen Farrell. I'm a certified hypnotherapist and an experiencer therapist. For about the past 13 years, I have worked directly with experiencers, contactees, and abductees.
It's credited to Ben Franklin, who said, "Do you love life? Then do not squander time, because time is the stuff life is made from."
Then it was off to the desert to learn more. So we have arrived at the site. We're going to learn a little astronomy and, just how to look out for UFOs.
Watch for jumping cactus.
It's also known as jumping cactus, and it seems to just jump on you. Don't even look at it long. I'm telling you, it has barbs to go in and hooks. Don't want to take anyone to urgent care. So stay away from the white cactus, far, far away. Yes, there's rattlesnakes. Yes, there's tarantulas if you're lucky enough to see one. Sometimes we have to just crawl right through here. They don't hurt you. Yes, there's scorpions. They're horrible.
In the parking lot has thousands of splotches that big from where the cars run them over.
Oh, nice.
And so if you go to the lights, there's like 20, there's 50, 100, you'll count thousands.
But don't let this man scare you. It's just like getting stung by a bee or a wasp. You're not going to die.
Sure, whatever you say. But when it came time for sunset, there's nowhere I'd rather be. It was a perfect night full of stars. And some people brought serious equipment. We even managed to find some scorpions. They weren't so scary after all. Then it was time for a good night's rest so we could be up and at 'em again Sunday morning.
Good morning, everybody. Last night was a blast. I'm so excited to be here and hanging out with my awesome Arizona MUFON friends.
Also, I've got a field kit in the back that you can look at that I use, one of my field kits with a lot of neat, nifty electronic stuff in it.
After some classroom learning, it was back to the desert for our practical test.
The practical is you guys proving that you have learned how to do what you're going to learn from John and Stan, teaching you forensic field work. And these guys are the best, so you guys need to consider yourselves super lucky that you're learning this from the ex-Navajo Rangers, because they are the best at what they do.
Who, what, where, when, why, and how. You want to be thorough in that investigation. When you have that sense, trust that.
And just so you know, that sixth sense, everybody has it to some degree. But it's like a muscle. If you use it, you can develop it.
Hoax is where it's obvious, where somebody has deliberately created an event and executed it. It means like they build a drone of some type, put a whole bunch of lights around the bottom of it, make it look like a flying saucer. And you got to find out where the truth lies.
I'm going to have 5 spots out here in the desert, all picked out and all baited with alien artifacts for you guys to find and bag and tag and collect correctly. And then you're going to prove that you know how to do that and fill out the forms the right way.
So, how did we do?
They did tag and collect all of it. Initially assessing the scene, safety was number one. Really, the focus was teamwork.
And they processed the site correctly. They made assignments.
Everybody has been following the guidelines religiously. They were number one. They did really good.
And to wrap it all up, we got our certificates of completion.
Thank you all for being here and having the right attitude and everything. It really, really helps. Thank you, Stacy.
We had a blast and even managed to get a few plugs for the show.
What's up?
What's up? What's up?
What's up?
Join me and Katie Grabowski and Krista Perno live every Thursday night from 6 to 8 p.m. Eastern right here on KGRA Digital Broadcasting. Tune in and find out what's up.
Outstanding. You might have seen yours truly in that video. I think I've been out there for, I think all but one of these boot camps to do instruction and teaching astronomy. I did a classroom segment and I did a nighttime skywatch segment, and people just loved it. Then we went hunting scorpions with ultraviolet lamps. Their carapace, their body actually just luminesces from the UV light striking it. It's really amazing. You can see them from 100 feet away. So if you get stung, it's your own darn fault. And they hurt when you get stung. There's certain kinds of scorpions out there that are worse than others. And all my time out there, going out there all these many years, I've never seen a rattlesnake except a dead one. And it was about, I'd say 100 feet, 150 feet from the observatory. So, but I'll say one thing, and this is something that I don't eat red meat because I don't like it, but rattlesnake meat is really like the best meat I've ever had in my life. I'm not kidding. You might now see there's people out there. I hear you. You're going, but no, it's really, really good, especially slathered in butter. Oh gosh, it's so good.
Tastes like chicken.
It doesn't taste like chicken. It tastes like rattlesnake, but there's no real way you can say what it tastes like. Everybody says tastes like chicken. Well, if it tastes like chicken, I just eat chicken. It has its own flavor. It's really good. Next to alligator tail, yes, that's another one I like. It's the best meat on the planet Earth. So whenever someone kills a rattlesnake, I say, "Did you eat it? Did you put it in the freezer and save it to get a nice rattlesnake fillet out of it?" Ew, no. It's like, ugh. And they say, "Well, they eat rodents." And well, lobsters eat dead things. And you love lobster? Oh, and it kind of changes their attitude a little bit. Anyway, I just think that it's pretty cool. The MUFON boot camp, and I was out there, and I then had to go after teaching astronomy out there in the desert. I went to the observatory to actually fix the optics. We had an optical problem like Hubble, and I fixed it. And now we're getting images that are to die for and not die from. Okay. And then I flew to Colorado, where they mentioned Katie Grabowski in that video. And I was with Katie and her Colorado MUFON folks, and I did a presentation for them. So it was really good. In fact, I just talked to Katie today, actually. She's got a lot going on out there. She's one heck of a researcher, and she's the perfect person to be, heading up the MUFON What's Up radio show, to be honest with you. She's a real good mover and shaker when it comes to that. So hopefully you can check it out. It's 6 p.m. on Sunday nights, Amanda? No, that's not Sunday nights. Thursday night?
No, trying to get them back here next week, are you? I see what you did there. Not Sundays. Tune in here for Sundays.
Right.
Thursdays, 6 Eastern.
Thursdays.
It's a 2-hour show.
Right. So 6 to 8 p.m. Eastern time is the MUFON What's Up app. The MUFON What's Up show. Yeah. So you see Krista Perno, you see Katie Grabowski, and you also see Katie Cook, who you saw in the video.
And of course, you can check out Krista Perno on Wednesday nights at 6 Eastern on iDetective.
That's right.
I know Marianne Robb comes to these chats often. Good friends with Tara Diulis, who joins us here Sundays. So
that's right.
It's a big family. So please, you're more than welcome to come join us Wednesdays, Thursdays, Sundays. Just don't leave. Just always stay logged into KGRA. You're safer that way.
Yeah, I have to tell you, this is kind of a little aside, but the KGRA people and the people I met at KGRA, going back to Race Hobbs at the time, Bill Skywatcher, you, Amanda, Daryl, all the people that run KGRA in the background that you never see, and then all the many hosts. Most of us have become good friends, because we actually enjoy what we do so much, and we respect each other and admire what we each do, in our own way, that we've become friends. And it's not uncommon for us to actually go to different places to see them and hang out with them. So, and many times you go to a conference, and guess what? You're going to run into one of us, because sometimes we're asked to speak at these different conferences, and so it's kind of fun to be part of this family, the KGRA family.
For sure.
So I'm really confident that we're going to end up, hanging here and hanging our hats here for quite a long time to come, or our form-fitting hats, as the case may be. Anyway, Daryl is sitting right there, and I think he's chomping at the bit to do some deep dives. We got a lot going on, a lot to see. So, I think Daryl might be ready. Thank you very much, Genghis. Genghis, again, longtime listener. Many of the people in the chat are longtime listeners and longtime viewers of SkyTour Livestream, as is Justin T. Yeah, huge dysfunctional family. That's funny.
We do. We have
Daryl,
the greatest community.
We do.
That's why we're here. Yeah.
We really do.
And
really do.
the community loves this next segment coming up from Daryl, by the way.
Yeah, they do. They do.
They do.
And so in our next segment, we call it Deep Dive with Daryl. He's going to take us in to an online planetarium that you all can get a hold of called Stellarium. You can also download it to your machine. And you can also use it to explore the universe on your own if you like. Or you can ask one of us, and we'll show you some really cool things as well. We use it to actually control the SkyTour Livestream West telescope. So there's that. So Daryl, are you up for this? You want to do a deep dive?
Yes, sir.
All right, let's go. I can't wait.
Okay, here we go, folks. This is the sky tonight from my location, just after sunset. You see the sun is just set over here. And it's interesting that it also shows Mercury close to the sun. I will get to more of that here in a little while. But I want you to see the sky tonight. Venus is that super bright thing in the southwest. Venus rounded the corner in its orbit around the sun recently, and now it's starting to move closer to the sun again. Venus is moving in our direction, so it's growing even bigger and brighter night by night now. It's tremendously bright. It's the brightest thing in the sky after the sun and the moon. If you can see it in a telescope, Venus has assumed a crescent shape. Sort of looks like a young moon facing the sun, but it's smaller than the moon because it's much farther away, and that will change over time also. But Venus is moving toward the sun. Now, a really pretty thing I would like you all to see. Okay, we've gone an hour later now. And you see that Jupiter, Saturn, and Venus are all in the same part of the sky. And Jupiter and Saturn are going to continue dropping closer and closer to Venus. I was under the impression that they were going to be in conjunction with Venus before it goes in front of the sun early next year, but they won't quite ever make it. But I'm going to show you what the sky is going to look like a month from now. There we will be. Venus will be lower, closer to the sun, but Mercury has popped up with it, and we'll get her up a little higher there. So at about 5:30 on December 28th, a month from now, we are going to have 4 bright planets in the same part of the sky. And that should be really beautiful. Mercury will be right under Venus, then Saturn, then Jupiter, all together. Venus, interestingly, we haven't been here in a few weeks. Venus has just come up and gone right through the teapot in Sagittarius, and it was that motion is because of our revolution around the sun, that 4 minutes a day thing that makes the sky crawl slowly from east to west night by night over the course of a year. Venus walked right through the teapot, and it's now sitting to its upper left a little bit. And this is a sure sign that summer has gone away and fall is coming and winter is coming when we see the teapot dropping off into the southwest after sunset. But there we go. The southern sky tends to go away faster because it's in the south. When we look up in the northern sky, which I'll talk about in a little bit, stuff tends to hang around a lot longer because it's in the north. And if it's at a certain altitude or latitude above the northern horizon, it never sets. But stuff in the southern sky goes away pretty quick. So here in a couple of hours from now, Venus is setting at 10 or 11 after 7 o'clock now. And Saturn and Jupiter, you can still see them, but they're setting early now. Jupiter is setting, I think, 10 o'clock or so now. We have been in Sky Tour live streams. We have been making our last visits for the season. In this part of the sky, we're going to start here, and then we're going to start walking up to the north and show you some neat stuff, hopefully. And Mark, going by the list I have, I'm going to start with the helix, okay? So get ready. And we're going to zoom in on Aquarius here. That's the water bearer. And we're going to look at the Helix Nebula.
Okay.
It's called Caldwell 63, but it's right below Aquarius, over the star Fomalhaut in the constellation Pisces Austrinus, which means the southern fish. And we zoom in, and we see this neat thing called the Helix Nebula. And Mark, take it away.
Okay, I want to just mention right away that there is a tremendous, there's a tremendous difference between the image you see here in Stellarium and the image that we actually took just the other day. This is the image we took the other day. This is the Helix Nebula. And I have it in in Photoshop, which I actually do image processing within. But if I was to actually just make it full screen here, that's a little better. So now you can see that the helix, this is what it looks like. And if you look all the way around this perimeter here, that star in the middle, this is a remnant of a dead star. This is called a planetary nebula. It's a star that has died. And you say, well, then why do we see it? It's because the remnant left behind is still very, very hot. In fact, it's so hot that it has radiation that's causing all the gas that it's ejected before to actually ionize and glow. See, and different elements glow a different color. For instance, hydrogen and neon and a few others will glow red like this. Oxygen will glow green like this. This is all stuff that was very likely in the star's envelope, the thing that was, around the core of the star. Only the fusion only occurs in the core of a star. Everything outside is just along for the ride. Okay, and that's the stuff that the star was made up from. And this is what we see here. So the helix has a bunch of interesting different elements to it. If we actually zoom in again. Zoom way in, and you can start to see. And Daryl, I was able to draw out some of these radial spikes that we didn't know we could actually see. It looks pretty cool here.
Yeah, it does. That is cool.
Yeah, and so these radial spikes that we see are all aiming at the star because the star itself is so powerful, has such an amazingly high output of ultraviolet energy and energy that can literally destroy this gas and push it away, that it's causing some of it to evaporate into these spikes that you kind of sort of see here. So this is what happens with these nebulae. The remnant is a white dwarf, okay? And as a white dwarf, this particular star will eventually cool into a black dwarf. Now, it's going to take billions of years for that to happen because the white dwarf is extremely hot. you got to keep in mind that that's the core of the star that was tens of millions of degrees. Okay. And so now, that would be something that we'd have to, worry about if it was near us and we were in that nebula. I mean, because this temperature of this nebula is pretty hot too. So, for instance, Ronald in the chat, ERRT Radio, asked, would that gas be really hot and the ship and would it melt the ship, basically? Yes, the gas itself you might be able to guard against, but the actual radiation from the white dwarf is what might actually destroy you. That radiation would be really, really, really intense. So that's a great question, Ronald. Thank you very much. But there it is. That's the helix.
The gas itself is so tenuous that you wouldn't even know it. If you were in that, you probably wouldn't even see it. It's so thin.
You might see a haze in the distance.
A little.
You might see a haze in the distance, but it's far, far less dense than the least dense cloud on the planet Earth in the atmosphere.
Yeah, I have to say, the helix here, this is a revelation since Mark did the collimation and tune-up his last trip to Arizona. We have looked at the helix before, but we are able to see detail in celestial objects that we were never able to see before the tune-up.
Yeah.
And this is a classic example. So much more detail.
It's just crazy. It's just beautiful. Incidentally, you might have seen a comment from Tara earlier. Tara, on vacation, still can't stay away, and she sent a comment in. Well, thank you, Tara. It's very nice. But I'm glad that you're not hanging out with us tonight because you know what? You're on vacation, so you just enjoy it, girl. There you go. So that's good. All right, Daryl, let's go to another object then because I think that because we're leaving the helix behind. See, there it goes.
Very good.
All right, let's bring you up
do
again.
you have NDC 253, Mark, or do you want me to go north?
No, I do.
Okay.
I'll go grab it because I don't have it. I don't have it in here. I'll just go grab it.
Very
but
good.
Go ahead.
Okay.
Show
I'm
it to
going to
people.
back out a little bit.
Yeah.
And we're going to move over to the star Difta. This is in the constellation Cetus. Difta's other name is Deneb Kaitos, which means the tail of the whale. And Cetus is the whale. I'll back way out first so you can see the whole constellation. Now, to me, it always looked like that's the tail and that's the head, but that's the head and that's the tail. And this is the star Difta, which is the tail of the whale. And if we zoom in some, and we're just above the constellation Sculptor, which I'll show you a picture. Let's see.
Keep it going a little bit because I'm trying to find it, Daryl.
Okay. Sculptor, well, there's a guy doing a sculpture, okay. And I believe this is it. Indice 253. It's sometimes called the Silver Dollar Galaxy. It is beautiful and very detailed. This is another one that looks 1,000 times better since the tune-up. And say when, Mark, and I'll just let you know.
I'm there.
Okay. All righty. Well, hand it over to you then.
All right.
This is called the Sculptor Galaxy, sometimes known as the Silver Dollar Galaxy.
Right.
If this galaxy was farther north in the sky, because this is far down close to the southern horizon, this would be about as popular as Andromeda Galaxy.
It would. And one of the things that we're gonna talk about tonight is the fact that everything we're looking at has all these dark lanes. See these dark lanes here? Okay, they are called dark lanes, and the reason that they're called dark lanes is because they're made not of gas but of dust. And where's that dust come from? Well, the dust comes from the continuous outflow of material from ongoing supernovae, explosions of big, massive stars. And these large, massive stars, when they get so big, they bloat so much that when they bloat, they actually end up having such a distended atmosphere, but so far away that they will eventually be so they're so big that the outer reaches are not as gravitationally bound to the star as they used to be. And so the slightest pulsation can kind of push them away. And those are the layers that will come off from some of these large stars. It's called mass loss. But the thing that also happens is that when these stars have such conditions, you can actually get molecules way, way out there because the temperature gets much lower as the star gets much bigger because it's farther from the heat source in the middle. And then you could have molecules of carbon in the outer atmosphere, otherwise known as soot. SOOT, soot, like in a fireplace. Those are carbon molecules, molecules of carbon strung together. And that becomes part of what we see in these dark nebulae. Okay, we see this dark dust in here. That stuff is carbon-based compounds as well as additional compounds of dust known as interstellar dust. And this particular galaxy has tons and tons of it, as you can see here. So that's the Sculptor Galaxy. And we'll take it back to you, Daryl.
Okay. I have moved ahead a little bit. Mark, on the list I have from you, M27 is next, Messier 27.
Okay.
Okay. So get ready. Messier 27 is called the Dumbbell Nebula. I sometimes call it the Apple Core. I did not think of that name. Other people call it that. But it's in the constellation Vulpecula, the little fox. And I'll show that to you. There is the little fox right there.
My little Vulpex.
Uh-huh.
That's right.
And so we're going to zoom in on Messier 27 now. It's all yours, Mark.
All right. Well, Messier 27 is a beautiful it's a beautiful planetary nebula, so named because they can be mistaken for planets in a small telescope because these don't look very large in a telescope. Okay, it's going to be kind of small like that. And if you kind of squint at it, it could look like a round object, could look like a planet. But as we zoom into Messier 27, what we notice is that, again, like the helix, there is a hot star in the middle. This is blue, and there's a reason it's blue. It's blue because it's so hot. Now, Amanda, I'm going to put you on the spot, and so don't panic now. But remember, we talked about the different types of stellar classes, the different types of stars and their properties. Remind us all about the different types of stars and what we see out there, and then I'll put this in that context.
Okay, well, there's a little mnemonic that I like, and it's been working for years, so it is foolproof. It goes from the biggest, bluest, and hottest to the smaller, cooler, redder, although the red ones are still quite hot because we're talking about stars here.
Yeah.
And the little mnemonic I use, so the first letter of each word is "Oh, be a fine guy, kiss me," or "Oh, be a fine girl, kiss me," depending on your preference. And those letters are designated for the size and shape and heat and color and everything.
That's right.
That's kind of hot.
Yeah.
Pun intended.
I would my guess, because it's more, to me, it's more green than blue, so I wouldn't say this is an O.
That's correct, because other things also are hot and blue. And like example, white dwarfs. White dwarfs are very, very hot stars because they're the remaining cores of formerly fusion active stars. There's no fusion happening in a white dwarf. It's residual heat that is actually radiating away, but it's so hot that what's coming out is mostly in the ultraviolet. And so the ultraviolet tends to do what we said before. It hits the atoms of the gas that used to previously be in the star that got pushed away as the star began to do its thing as it got older. And as it pushed this stuff away, the star shrunk in the middle down to this white dwarf. A white dwarf is about the size of the Earth, by the way. And from the distance this is, which is, is this like 1,600 light years away? I'm trying to remember. It was like maybe 2,000 light years away. It's actually reasonably far away. And we can still see the white dwarf in the center. That's pretty cool. That means it's a very hot star to be able to show as a point of light that's that bright from this distance. It's adding up on our sensor for the camera, making this bloated blue image. It's really a point light. A point light. All stars are points of light. But on film and on sensors like this, they look like bloated round objects. If you could see stars the way that they normally would look, you would say, where are the stars? You almost wouldn't be able to see them on a computer screen, okay? Because they wouldn't show up because they're just points of light. So that's something interesting about stars that we consider, okay? So this is the Dumbbell Nebula. And just like we said before, this particular nebula has an interesting, what should we say, evolution, because this white dwarf in the center, ionizing all the gas in this cloud that used to be the star's envelope, the thing that was along for the ride that I talked about before, all the gas that's outside the core where the actual action was going on. And now it's been ejected from the star, but the star shrunk down to this white dwarf, and it's so hot, it's causing all this gas to ionize and glow. Oxygen typically glows this bluish green color. Hydrogen can typically glow red, okay, along with neon and some other elements, okay, strontium and things. And so we can actually get some really interesting lines like this. Again, as Daryl pointed out before, since fixing the telescope, we have unprecedented detail that we can see inside these nebulae. And we're not done yet, because I'm actually trying to work on ways to get even more. Oh yeah, it's going to be a phenomenal thing coming up. So there you go, Daryl, and we'll set you back to you. And why don't you take us down another path, and we'll head on out.
Okay. Well, here we are, and there's the dumbbell. Now we're getting back up into the northern part of the sky now. Here is Cygnus, the swan, and I'll show you the swan. There's our old friend Alberio, the double star. Here's our old friend Deneb, the tail of the swan. There is the Northern Cross. And right here is the North American Nebula. Mark, did you want to spend any time right here or move on to the list?
You can head on to the list, because I have these nebulae, but I didn't load them up. They're right here, but rather than waste time, we can just plunge on, because there's so much more to see.
Very good. Okay. Next on your list then is M31. We're up in the part of the sky north of Cygnus. All this is moving to the west now too, and we can see it longer because it's farther north, but we still have to grab it before it's too late. It's Cepheus the king, Cassiopeia the queen, Andromeda their daughter, and her boyfriend Perseus. And here is M31 Andromeda Galaxy, right in Andromeda.
And the most impressive galaxy.
Yes, I'll hand it over to you.
All right. When we look at this galaxy, I just want to show you. Now, first, you're going to look at this and say, what are we looking at? What is this? Well, what we're looking at actually is a very zoomed in image, okay, of the Andromeda Galaxy. If we zoom out, you can see what we have actually accomplished here. We have actually accomplished creating an amazing image of the Andromeda Galaxy right here. This image right here, we can see individual globular clusters, because globular clusters are basically like exploding snowballs of stars as seen in these other galaxies, including our own. Okay. And these clusters are such that they orbit the galaxy. They're called halo objects. Halo, Halo. And as a halo object, they orbit the galaxy, and sometimes they pick up stars, sometimes they leave stars behind. But the bottom line is there are unique features to these galaxies. And so when we zoom in, we can see some of these faint objects here. Some of these faint objects like this and this and this. These are all globular clusters in this star, in this galaxy. So, for instance, let me say with this pointer, so now you can see it. There's a globular cluster. There's a globular cluster. There's one. Here's another one. Here's another one. So we actually see globular clusters. Now, the other thing we see is something that we're going to spend some time on talking about, and that is the hot young stars. Where are those formed in a galaxy? Well, when we look here, okay, let's get rid of that. When we look here in the galaxy, we see that there is a tremendous disk of stars, and it's in there where you see all these hot young stars. In the middle are the older stars, There's older within the spiral arms of this galaxy, which you can see here very, very clearly. In these spiral arms, you see all this dust. And then you see things like this right here. This guy right here, this is what's called a stellar nursery. We've seen these stellar nurseries. Many of you are familiar with the Orion Nebula, okay? The Orion Nebula is actually a stellar nursery, okay? Here's the Orion Nebula. We image this with SkyTour Livestream, okay? And that's a stellar nursery. You can see that with your eye. Well, this is an example of a nebula that's a lot bigger than the Orion Nebula is in our galaxy. The Orion Nebula out there is probably like this guy right here. And if you can't see it, well, then we zoom in more. Okay, so we zoom in a little bit more. And now you can actually see this guy right here. This right here is probably a region that's about the same size as the Orion Nebula is in our galaxy. And I tell you, it's unprecedented how much detail we can see. But now if you come down to the bottom edge of this galaxy, which I should say is not really the bottom edge, right? Because we're looking at the whole galaxy. But let's go down to this bottom area. And one of the things you can see now is this hot blue collection of stars. Okay. And then you see another one here, another one here, another one here, more here, more here, more here. These are called OB associations. Remember when Amanda was talking about OB, a fine girl, kiss me, that OBAFGKM? That is how we classify stars in terms of their color. O's are hottest and bluest, as she said, and the M's are the coolest and reddest. Well, the O's are also the shortest lived. They don't live a long time. Neither do the B's. So these are a lot of O and B stars here. They're the bluest stars in the universe. And when you see them here, these are probably all O stars in here, or a good deal of them. When these go supernova, guess what they're going to do? They're going to litter the cosmos with their guts. I hate to say it that way, but that's how it is. And when they do that, they're going to litter it with all kinds of elements that are in the periodic table, right? The periodic table is the same throughout the universe, as far as we know. And so we'll see so many different objects out there. And these blue stars, being hot and young, they only live a few million years. To give you an example, when you look at the constellation of Orion, you see the belt of 3 stars. Everybody knows Orion and the belt of 3 stars. Well, that belt of 3 stars is fascinating because when we see the belt, we're seeing the stars as they exist for all of us for generations. Many of us have seen these for hundreds of years. It's always had 3 stars in the belt. Well, guess what? Lucy, Australopithecus afarensis, the precursor to humans, all right, when Lucy looked up at Orion, Lucy saw some very markedly different things looking up there. She saw Betelgeuse, which is the bright red star in the top left. She didn't see it as a red star. It was a bright blue star. And when Lucy looked up at the belt of 3 stars, she didn't see 3 stars. She saw maybe 1, possibly 2. Okay, because some of those stars had not formed yet. Because they're O-type stars, they live a few million years. And some of the stars are under 4 million years old. Lucy is about 4.2 million years old. So you see, on the scale of human life on the planet and the scale of human development on our planet, of our species, you can see that the universe has changed. But it changes in a manner that we won't necessarily see, and not in our lifetimes. We're fortunate enough to watch a supernova in a Messier object called Messier 66. Daryl, I think you remember that, right? We looked at supernova in Messier 66 one time.
Yes.
Yeah. And we're also fortunate enough, and you were there for this too, to watch a meteor strike the moon during a lunar eclipse. We saw a flash, and that was a meteor striking our moon. So it shows you the universe is a dynamic place. It's still doing all the things that the universe has been doing since antiquity and well before humans were here. So this particular object, the Andromeda Galaxy, has been a staple for many people who look for amazing things in the night sky. And as we slide through it, you can see another hydrogen stellar nursery region here. And if we keep going, you see there's one here. There's several small ones over here. There's one there. And there are some stars in here as well, but in these spiral arms, that's where you see these complexes that have some really interesting stuff going on. Here's a gigantic nebula in this galaxy. This galaxy, by the way, is 2 million light years away. That means
2.5.
Yeah, and that means that it means that this light that we see here has been coming to us for over 2 million years. So if you go back in time and say, what was happening on Earth when the light I'm seeing right now left this galaxy? That puts it into perspective for you. It really does put it into perspective for you.
M31 is another. Since the tune-up of the telescope during your last trip to Arizona, we see so much more fine detail in this than we ever did before.
It's
that
stunning.
Part in the lower right is just so much different. I don't remember ever seeing it in such detail before. That
you can see the separate
big bright blue
blobs.
OB association,
Yep.
and everything all the way to the edge in the picture. If you zoom out in that too, folks, so we can see the whole galaxy, Mark, there are actually three galaxies in that image. You've got the big one, M31, and that one at the upper right he's circling is M110, Messier 110, and M32 right there. Those are both satellite galaxies of M31.
Yeah, and one of the things that we notice about some of these giant spiral galaxies, and mind you, this galaxy is way bigger than our galaxy. This galaxy could contain up to 1 trillion stars. For the record, you know how many stars you see in our Milky Way. They're endless, it seems. Well, we're kind of a rather moderate to smaller size galaxy, actually, and we only have perhaps 150 billion to the 1 trillion. And oh, by the way, the Andromeda Galaxy is heading right for us. In a few billion years, it's going to pass into our galaxy. And when that happens, we see what it does to other galaxies around the universe when galaxies collide. It doesn't spell the end of anything. It doesn't destroy lives. It doesn't destroy civilizations and life. In fact, the life goes on unabated. It doesn't even notice it because the distances between the stars are so great that, yes, it'll disrupt the overall shape at a cosmic level of the galaxy, and that will definitely change, okay? But what happens is when they pass through, then they become gravitationally bound and they kind of orbit each other and they make a new galactic shape of some kind. And we see cases where we see galaxies in the middle of collision. One particular set of galaxies are called the antennae, like bug antenna galaxies. I can't wait to image the antenna galaxies for you and show you what that looks like, because that'll be just spectacular.
Oh, yeah.
Okay. But the other thing, too, is these galaxies are what we call, as Daryl mentioned, companion galaxies to the Andromeda Galaxy. Well, we have some, too. Okay. When we look at our galaxies, we have actually several galaxies that are associated with us. The two that people know are the Large and Small Magellanic Clouds. Those are dwarf galaxies that are orbiting our galaxy. But there's another dwarf galaxy that's also part of this mix as well that might be associated with us. So galaxies can be alone, but not necessarily always alone, as you can see. And, I don't know how true this is yet, but I'm working on this, and Daryl has noticed this too. When you look at the Andromeda Galaxy, one of the things we notice is that this end looks like it's tipped down a little bit, and this end looks like it's tipped up a little bit. Now, is that a warped disk? We have seen warped disks of a galaxy that has a warped disk is one that we're going to image later in the year. That's called M51, the Whirlpool Galaxy. That one has a very warped disk by studies. I think this is a warped disk as well. Maybe because of the orbiting of these particular galaxies.
Or
these
maybe
galaxies,
because of the next galaxy on our list.
That's correct. It could be. And there's another, but these two are right in its proximity. Mm-hmm. The next galaxy on our list, though, which Daryl will show you in a second, is one that is actually possibly and foremost one of the most interesting objects I've ever seen. Yes, Andromeda is great. But Andromeda is a fairly tightly wound spiral. The arms are very regular. I prefer the galaxies that are just a plain mess. Okay. And that's what we're going to see now.
Well, hold on. It's a great tease and a great segue, but we have a question from chat. Just
Fantastic.
before we go too far, about us passing through Andromeda. Very
Okay.
interesting question from Lewis. Will the two black holes from both galactic centers merge?
Maybe.
Then
Well,
what
that's
happens?
interesting. Let's explore that concept for a minute. Consider this: we imaged the black hole for the first time a few years ago, and the way it looked is exactly the way it was predicted to look by Einstein, and by astrophysicist named Kip Thorne. I sat with Kip Thorne and we talked about black holes one time years ago, and he was talking about the structure of black holes and what they do. And what we found in the image of this Virgo galaxy, Messier 87, that's the designation, was that for all of its distance, we could image the black hole because we used the entire Earth as a telescope, because we had a bunch of we had a bunch of dishes, radio telescope dishes all around the Earth. And as the Earth rotated, it effectively made an 8,000 mile diameter, because that's the diameter of the Earth, 8,000 mile diameter telescope. And that gave us a lot of resolution. We could see the black hole in the center of Messier 87. What we saw astounded us. The size of the black hole wasn't the size of the sun, wasn't the size of the Earth's orbit. It was several multiples of the size of our entire solar system. Now, wait a minute. How could that be? Messier 87 is one of the most massive galaxies in existence. But how did it get that way? How did that black hole grow in such size? Now, I know people think black holes are tiny little individual points, but there is what's called an event horizon, the point at which light can't get out. It just circles forever inside. And that event horizon is massive on this black hole because it has so much mass in it. How did it get that mass? How did it happen? We're not privy to the past. We can't see, and there's no real evidence. There are some interesting jets sticking out of this thing, jets of high energy materials shooting out at high speed.
We've seen them.
We have in this very telescope, but and we'll see them again. But what actually causes the galaxy to have such a massive black hole? Acquisition of mass. Well, how did it acquire so much mass? Maybe, Lewis, it's because that particular galaxy could be the end result of multiple collisions over billions of years, long before we even existed, perhaps, of other galaxies. And maybe, as you suggest, there was a merger of multiple supermassive black holes that are at the center of these other galaxies. Maybe that's what happens. It's a theory that I've been working on and thinking about for a long time, that maybe at the center of all these galaxies, that supermassive black hole can indeed merge. Now, colliding black holes also, can cause tremendous disruptions too. And that's something that we have to be cognizant of. So those disruptions are things that can be the most massive cataclysms in the universe. And so we don't necessarily want that to happen, but they can also possibly merge. And if they do, then we would see that maybe we have a new supermassive black hole that's much bigger than we expect it to be. Thank you, Lewis. That's a fantastic question. No, I don't know.
Kathy asks, Kathy Pernasek, will the Andromeda Galaxy tear the Milky Way apart? They will certainly interact. Mark mentioned the antennae galaxies earlier. I wouldn't say Andromeda will tear the Milky Way apart. They will certainly affect each other in a big way. I wish I had a picture up ready to show you of the antenna, for instance.
And I don't.
You will see the two galaxies. They will kind of wrap around each other and spray pieces all over the place. And it will look really cool when that happens. We won't be here to see it, though.
Well, and even if we were, Daryl, it happens in slow motion to the scale of human life. So for the entire existence of thousands of years of human life, if that was happening here, it would look like the sky is almost unchanging to them. It's all slow motion, but the universe has time in abundance.
Oh yeah.
What's going to happen to our gravity? Is there going to be any change there?
No. In fact, we won't even notice that the people on the future Earth, the far future Earth, won't even notice that anything's happening. They're not going to suddenly being tugged away, pulled away, and ripped from the planet. Not going to happen. We're just going to see newer stars in our neighborhood. And that. Go ahead, Daryl.
I'm sorry. Go ahead.
I was going to say, we'll just see newer stars in our neighborhood. And we'll recognize that we're under collision, of course. And for eons of time on Earth, people will just be here thinking, well, we're two galaxies in collision. And for them, that'll always be their universe. And that'll be the way it goes on from time to time. And it'll never change for millions of years. And over millions of years, there'll be subtle changes that we notice. For instance, we orbit the galaxy. We orbit our galaxy right now. We have gone since 4.6 billion years since we were formed. We've gone around our galaxy only 20 times. Okay. So it takes 230 million years, 250 million years or so to go around one time. So that will be disrupted. Our orbit around the galaxy will change because the structure of the galaxy may change. Maybe the collisions of galaxies lead to galaxies like we see here in Andromeda, elliptical galaxies. Okay. Maybe that will lead to a different kind of galaxy. Undoubtedly, we see the answers all around the universe. We just haven't recognized them yet. That's what's so cool.
You talked about gravitational interactions, and we seeing Andromeda there, that at the upper left and the bottom right, that the edges are kind of warped. If I can move on to the next object, we may show you what else may have done it besides those two satellite galaxies.
I think that's a great idea. Go for it.
Very good. Okay. Let's see. Here we are. This is M31 and Andromeda. And close by, right here, is M33 galaxy, constellation Triangulum. Now, M33 is not far from Andromeda. And physically, this is true. They have possibly interacted in the past. And Mark, I will hand it over to you. And when we see M33, it has obviously been messed with, distorted, you might say, maybe from M31. It is generating a tremendous number of stars.
As you'll see.
See.
So when we look at it, here, okay, for instance, we look at this is Messier 33. You immediately notice something different. It looks like you're it looks like the unkempt brother, okay? The one whose hair isn't combed. Everything is all over the place. Now,
that's me.
That's me. Well, look at me. I got my hat on. That's the way of these particular galaxies. Now, we classify spiral galaxies in a number of ways, okay? We have spiral galaxies that are denoted with a capital S, okay, capital S. And the capital S is the capital S is a designator that basically says spiral. And then, okay, galaxies like this one, okay, these have spiral arms that are just a little bit unkempt, right? So we call this a capital S with a little letter after it, the letter C, right? As you can imagine, there's an SA, there's an SB, and an SC, capital S, little a, capital S, little b, etc. And Andromeda is a capital S, little b. It has tighter spiral arms. It might actually be an AB. It's kind of a combination of the two. And then this one is an SC. It's a mess, okay? But when we look at it, one of the things we do see that is really interesting is all these red areas. All these red areas in here. This is an amazing galaxy. This right here is known. We actually don't usually classify objects in other galaxies like we do in ours. We have, NGC values, which are catalog values for something called the New General Catalog. This is given a designation of NGC 604 because it's so prominent in this galaxy. And dozens of other objects in here also have those. Okay. That is the very interesting factoid about this particular galaxy. you'll see the arms again, the blue arms. These blue arms are of course, the unkept brothers. Okay. The spiral arms, you see them going out like this, okay, out like that. And they seem to be twisted in a variety of ways. They're not even. This one goes out gradually. This one curves sharply. This one really curves sharply. Then this one goes gradually. And then this one kind of zings around kind of gradually. One thing to notice also in this galaxy are these areas that look like they're bluish green. There's one there. There's one there. Okay. There's one here. Okay. In fact, if you zoom in on them, you can actually see that there's structure in there. There's like loops inside here. And there's one here. This one here actually has more structure inside of it than you can see. And then we come down to the bottom here of the galaxy and notice that there's an even more interesting location, like right here. You can see a long extended loop right there. This is stuff that is indicating remnants of a supernova. Here is another one. Look at that. Right. We see the central star that exploded. Maybe that's going to be a hot neutron star in there. Maybe that's just a star that's nearby in the field, or maybe that's a dense area of expanding gas. But then we see this spider-like explosion outward of stuff that's coming out. These objects here, by the way, these are just artifacts of the camera, not to worry about. So that said, when we also look at this galaxy, another thing we see is all this dark dust. Look at all this dark dust. That dark dust is outrageous because this dark dust tells us that there's been a lot of supernovae in this galaxy. Here's a beautiful nebula region. This here and this here are probably on the order of what we have here in our galaxy called the Eta Carina Nebula. Okay, that's one of the largest. It's actually not in our galaxy at all. It's a companion galaxy. But it's got this beautiful, beautiful, large size to it. And same thing here. So these are areas where there's rapid star formation, and everything in here that looks like a distended red thing or a fuzzy red thing, these are all star forming regions. And in this galaxy, all these blue areas are areas that are hot, young stars that have been born. The center of most galaxies are yellow because those are older stars. All right. The hottest, youngest, as Amanda told you earlier, are blue. And the older ones tend to be yellow toward and into red. Now, not that there aren't a lot of red stars. You can see some. There's one right up here. Okay. If we zoom in, okay, that's a red star right there. This is a red star. This is undoubtedly a foreground object in our galaxy. If you look at all these stars, all these larger round dots, that's in our galaxy. These are in our galaxy, and we're actually looking through all that. It's like a veil, a thin veil of stars, to a much further distance away. You can't see the individual stars of this other galaxy, not unless you zoom way in and start to really, really try to look deeply at some of these areas. Then you get a hint of the other stars. But if you can see stars, it means you're looking at our galaxy. Yeah. So this is a galaxy.
When you look at that galaxy, there's just a tremendous amount of star formation going on in there. And that is a classic sign of interaction. Yep. The say past M31, well, that caused the gas and dust to mix up and start a lot of new star formation.
That's right.
And that's what we're seeing there.
Yep.
We're about ready to go, Mark.
Yeah, we are. So I just wanted to leave you guys with one more image that I think is kind of cool. Daryl, great job doing a deep dive. That was fantastic. And to give you guys an idea of the kinds of things that you might be able to see when you come here and come to SkyTour live stream, how about digging that? How about that? This is called the Rosette. This is a winter object. We're going to see a lot more of it. But this is a beautiful object, and it's a star-forming region, and we'll see many more such things when our winter sky approaches. Beautiful. So I want to just wish you guys all a wonderful evening. Thank you so much on behalf of Daryl and Amanda. I'm sure I speak for them when I say we loved having you. And we'll deep dive into the deep night sky the next time we talk. So you guys have a good evening, and don't forget, keep looking up.
Except while you're driving.
Exactly. Good night, everybody.